Today in Chem 100, we're going to introduce the topic of gases. And if you go into Brightspace and you're looking for documents that pertain to this particular chapter, you're looking for PowerPoint slide set, looks like that. You're looking for review document, which looks like that. And if you need it, the worked problems for the review document. Okay. After gases, we're going to look at gases. This chapter is the only chapter we're going to cover in Exam 7. Then we're going to do acids and bases for Exam 8 and redox reactions, which probably doesn't mean anything to you now, but it will, for Exam 9, and then we'll have a comprehensive final exam at the end of the semester. All right. So there's the outline as usual. Why do we want to study gases? Chronologically speaking, as the modern scientific era was opening up in the middle 17th century, the technology and what scientists understood of nature was concentrated in the study of gases. They were able to measure the volume of gases, the mass of gases, various other phenomena related to gases. It was later that what they learned from gases, they would also be able to apply to liquids and solids. But gases came first. And with our study of gases, we're going to introduce some concepts that stem from our earlier study of how science works, and this will be a practical approach. When I talked about observations, and then you form a hypothesis, and then you test the hypothesis, you draw conclusions, decide if the hypothesis is a good one or a bad one, and then you circle back and try again. And out of that came laws. We're going to study the gas laws first. And then from that, actually decades of experience, came the theories and the models that followed with the theories for how gases work. These were considered fundamental breakthroughs in chemistry, studying gases, and we still use gases for fundamental research. And there's a very good reason for that. Remember, the nature of a gas is that it has no definite volume, has no definite shape. So it completely fills the container. As long as the container is sealed, it will fill the container with whatever you put into it. If it's not sealed, then it'll just mix in with the air outside the container. Another characteristic of gases is that two or more gases together in a container form a homogeneous mixture every time. In other words, all gases mix to form a solution. And it just makes sense because gases, relative to the distance between the gas particles, they are very, very small. There's lots of room in there for other gases. So you put two of them together, they just perfectly mix. We do know that gas confined in a container exerts pressure on the walls of the container because we can measure that pressure with an inserted device. a pressure gauge of some kind. So what does that mean? That means the gas particles are moving. They have kinetic energy. They have mass, they have velocity, and when they strike the measuring device, it registers a force. And we quantify that force in terms of pressure. Now, force is an extensive property. Whereas pressure is an intensive property. That just means that force gets bigger or smaller with how much of it there is. Pressure doesn't change. It's force per unit area. So when we ratio force to the area, the force over a given area, and we take the quotient of those two values, we get pressure. And if the area goes up, the force has to go up also to maintain this as a constant. So that's one of the first measurements that we make relative to gases is the pressure. Now in SI units, the pressure is derived from newtons per square meter. Newton is a unit of force, and it's a standard unit of force from the international system. Now, the Newton itself is not a fundamental unit. It is a derived unit, and it's derived from Newton's second law of motion. Right? Newton's second law of motion says if you apply a force of a given amount to a mass, it will accelerate at that value. So if we say this force is equal to mass times acceleration, the standard unit here is kilograms for mass, and acceleration is meters per second squared. Right? Acceleration is a change in velocity. Velocity is meters per second, and if it changes over time. So we have to add another time unit in there, meters per second squared. So this kilogram meters per second squared is equal to the Newton. Right? These are each fundamental units. This is a derived unit. And this is also a derived unit. Newtons per square meter is 1 Pascal, equals 1 Pascal. Now the value to the, I've mentioned this before, but I'm going to say it again. The value of the international system is that all these units are interchangeable in some form or fashion. So if you have a calculation that has in it kilograms, meters, and seconds, but you're given a value of pascals, then you know what the equivalent of that Pascal is in terms of Newton meter squared. You know what newtons are in terms of kilogram meters per second squared. You can substitute those in there, and then your calculation can cancel units if necessary. All right. Gas pressure is one of those concepts in which there are a number of different units that have been adopted over time. This is the standard. But for practical purposes, we're going to use a different one called atmosphere. 1 atmosphere. And it is interchangeable. It has an equivalence with pascals of 101,325 pascals. Okay. So if we know how many pascals of pressure, we can convert to atmospheres and vice versa. If we have atmospheres, we can convert to pascals. Now, atmosphere has been standardized so that it's not actually always the pressure at sea level. atmospheric pressure at sea level. Right? We standardized it as an average value, and then everybody agrees upon what 1 atmosphere is. It also can be equated with other units of measure. If we have a barometer, which was invented by Evangelista Torricelli, and that's one of the reasons that gases were studied first, because now with Torricelli's barometer, we could adapt it to measuring the pressure of gases in any container. So 1 atmosphere is 760 millimeters of mercury. You have to understand what a barometer is in order for that to mean something. And I've got a slide coming up. We're going to talk about it in just a minute. We also say a millimeter of mercury in this context is given a unit of torr in honor of Torricelli. So it's also 760 torr. Okay. Now, if we want to convert to the imperial system, it would be in units of pounds per square inch. And that's 14.69. So all of these are equivalent, right? The atmospheric pressure on average at sea level is 1 atmosphere. It's also this value in pascals, millimeters of mercury, torr, pounds per square inch. All right. So here is Torricelli's barometer. It's a very simple device. He chose mercury, liquid metal mercury, because it is liquid at room temperature, and it has a very high density. He could have used any liquid, right, to measure air pressure. All you have to do is take a tube of uniform diameter, seal it off at one end, turn it up and fill it with your liquid, and then stopper it, invert it, and submerge it in the pool of the liquid. And then you'll see it drop. Right? It'll drop a certain amount, and the distance from the surface of the liquid to the top of the meniscus here, this is a convex meniscus, is the measure of atmospheric pressure. Air pressure is bearing down on this pool of liquid, and it's forcing that column up a certain height. And it doesn't matter what size that pool is, because pressure is an intensive property. All right, so the pool could be this big, it could be this big, whatever. Also, you may notice that if you have matter in a space and then you remove the matter, what do you have left? You have a vacuum, right? There's nothing there for all intents and purposes. So this was effectively the creation of the first vacuum in the top of that tube. Also, once the barometer was invented, other scientists latched on to this instrument, created their own instruments, and they started experimenting with them, seeing what changes they could measure. One of the changes you can measure is you can take your barometer, throw it in the back of your ox cart, and go up the mountain. And when you get to the top of the mountain, you'll notice that the level of the mercury is lower. So it's logical to reason that there's less air above you pushing down on the pool, is why the column is not supported at a higher level. It's down. If you take it and go down to sea level or below sea level, you notice that the column of mercury rises. So that means that there's more air above you pushing down on that pool. There were also some scientists who just took one of these and set it on his desk and just watched it over time. And pretty soon it was noticed that when bad weather was coming in, stormy weather was coming in, the level of mercury dropped. We call that low pressure, atmospherically speaking. And then when the weather passed, the mercury rises back up. Fair weather means high pressure, bad weather means low pressure. And we still use that concept in meteorology today. Now, we can also adapt the barometer to measure the gas pressure inside a container. And that device is called a manometer. Right? Here's a schematic of a manometer. In this case, the tube is connected to the container, and it's open on the atmospheric side. So what you have is air pressure pushing down on the column. Also, pressure from inside the vessel is pushing on the other side of the column. So you can measure the difference between those two, but you also have to have a barometer to measure what is that pressure that's pushing down on the right-hand arm of the column. And then by difference, you can tell what the pressure is inside the vessel. This is a manometer. Oh, by the way, if you've ever taken your own blood pressure or witnessed blood pressure being taken, you have seen another modification of the manometer. It's called the sphygmomanometer. And it's got a cuff, right? Put it around your arm, usually the left arm. It's closest to the heart. And pump it up, and a device measures the pressure in that cuff in millimeters of mercury. Now, some doctors' offices still have the mercury sphygmomanometer on their walls. They don't use them anymore. They're just there for decoration. But once you pump it up, then it's feeling the pressure of the pump of your heart, right? And it changes the pressure inside the manometer. Okay, so what they're listening for are the Korotkov sounds. I think there are 5 of them, I believe. They're listening to 2 in particular. As the pressure drops, the first sound they hear, the whooshing sound of your blood, is the systolic pressure, the higher pressure. And then at the end, when the sounds start to fade away, is the diastolic pressure. I think that's right, the low pressure. So we use a modification of the barometer to measure blood pressure. Okay. So what are we witnessing here? Notice on the left-hand side, this can is open, and we just put some water in it, heat it up, boil the water, and what the water does is it drives out all the atmosphere, and there's nothing left in the can but water vapor, right? So then we put a stopper in it and turn off the burner. And as the can cools, what happens to the water vapor? As it drops below 100 degrees Celsius, it condenses. Well, when it condenses, it takes up less volume, right? We change a gas to a liquid, and that space up there is no longer occupied by gas, which is pushing on the walls. So there are 2 forces in there in the beginning. The gas, the water vapor pressing outward, and the air pressure pushing inward. They're balanced. But when the water vapor condenses, now there's no pressure on the inside, and the outside pressure collapses the can. I've seen this done with a one of those railroad car tankers, big tankers, and they've filled it with I'm not sure what they fill it with. They either evacuate it or they fill it with water vapor and let it cool. But once it's sealed up, the pressure on that tank, eventually the whole tank collapses, right, with a big bang. All right. So here's an example of pressure conversions using our equivalents. Remember, if you have an equivalence of 2 units, you also have a conversion factor. Okay, so if we have a measured pressure of 2.5 atmospheres, what is that in terms of torr and pascals? Right? Right? We use our logical process. What's the question? The question is convert pressure atmospheres to torr and also convert it to pascals. This is what we know. 2.5 atmospheres is given. What do we need? We need conversion factors, an equivalent statement for our units. Right? So if we're going to convert to torr, we need a conversion factor, a quotient, that has the desired units in the numerator and the canceling units in the denominator. So we cancel the atmospheres, multiply the equivalent value times 2.5, and we get 1.9 times 10 to the third torr. All right. Now let's convert it to pascals. Right? 1 atmosphere, we know what the conversion factor is, and we convert it to 2.5 times 10 to the fifth pascals. Now, did the gas change? Right? Did the gas say, oh, well, you're changing my units. I think I'm going to have to decrease my pressure. No, it's the same pressure, no matter what the units are. Right? The gas didn't change. We just changed the units of measure. And notice that if the unit, well, let's do it this way. If the number gets bigger, then the unit gets smaller. So a torr is much smaller than an atmosphere. It takes 760 torr to make 1 atmosphere. So the torr unit must be smaller than an atmosphere. All right. Vapor pressure over a beaker of hot water is measured as 656 torr. How do we know that? We know that because we have a barometer on the wall, and it measures the atmospheric pressure, so we know what it is. What is this pressure in atmospheres? All right, our conversion factor. The canceling unit is in the denominator, and the retained unit is in the numerator. 1 atmosphere per 760 torr, and that gives us 0.863 atmospheres. All right, now we're going to look at the gas laws. Those laws that were determined over time to apply to any gas. That was one of the advantages of studying gases, because it really didn't matter what gas you were studying, they all behaved similarly with respect to these gas laws. Okay, Robert Boyle was an English scientist in the mid-1600s, and he took the idea of Torricelli's barometer and modified it. So he created what's called a J-tube. It's just a long tube that he heated and bent into this shape. And he put mercury in it. And it pooled up on the bottom. And he put some more mercury in it, it pooled up. When it touched the inner wall here, that trapped the gas inside. So now he's got the same amount of gas, the same number of moles of gas in this space, and that will not change. Right, so that's constant. The temperature is relatively constant too, because this experiment doesn't take very long, so the temperature is not going to vary that much. Okay, this is Boyle's law. Coming up, what I want to do first is tell you something about gases. If we want to describe the behavior of a gas, the physical behavior of a gas, we need four factors, four variables. We need to know the pressure, the volume, temperature, and the number of moles, how much of the gas there is. This temperature has to be in Kelvin. Right? Remember, degrees Celsius plus 273 is Kelvin. And the pressure and volume can be anything. So, what Boyle noticed was, as he kept adding mercury, he noticed that on this side was different than that side. Right? It was different by a certain amount. Let's see, that's not right. Yeah, it is. It was different by this change in height. Okay, so that represented a difference in pressure between here and here. Right, the pressure out here is 1 atmosphere, or 760 millimeters of mercury, and the difference here would be plus delta H, and that would be equal to the total pressure on that gas. Okay, he kept doing it and measuring this distance. I think the slide is the difference is L1 and L2. So what he noticed was that as he added more mercury and increased the pressure on the gas, the volume decreased. The height, the length, or the delta H got smaller and smaller. Right? As this goes up, this gets smaller and we get closer together. Right? That value gets smaller. Okay? So he reasoned that the pressure, and he could say the height was related to the volume because the tube was a uniform diameter. And remember, the volume of a cylinder, is height times area. Right? So if the area, the diameter of the tube, translated into area, is uniform, then you can use height as a measure of volume. It's related to volume, directly related to volume. So what he noticed was that the pressure is inversely proportional to the volume, which means pressure times volume was a constant. Right? Whenever you have a product of two variables equal to a constant, they are inversely proportional to one another. That's a constant. If this goes up, that one has to go down. Vice versa. That's an inverse proportion. All right. And here's an experiment. And what we noticed is that as if we measure the pressure, inches of mercury, I forgot that one. 1 atmosphere is also equal to 29.92 inches of mercury. That's another unit of measure. So as we increase the pressure through experiments 1 through 7, we notice the volume decreases. If we multiply those together and round them to, say, 3 significant figures, right? Because pressure is in 3 significant figures and volume's in 3. So if we round them 3 significant figures, we get a reasonably constant value. Right? That's Boyle's law. If we graph it, we put it on a graph, All right. Actually, this graph is backwards because we're changing the pressure. I am the experimenter. I control the pressure by adding mercury. So pressure should be here. And volume is the response. Atmospheres, let's just say liters. As the pressure increases, the volume decreases. So we get values here like this. And it produces a curve. Now that's an inverse proportion, but it's not linear. Right? And that's characteristic of two variables in a product equal to a constant. They always produce this type of curve. In mathematics, that's called a hyperbola. Okay. The line is sloping from upper left to lower right, which means it's decreasing. It's a negative slope. Negative slope. Now it's not the same slope everywhere, right? Here's a different slope. Here's a different slope. We measure the slope of the tangent to the line. So the slope is changing, but it's always negative. Okay. This is not a very practical way to solve problems. So if we have a situation where we're giving conditions of pressure and volume at this place, and then we change one of them, say we change the pressure. Well, if we change the pressure on the same amount of gas at the same temperature, then what's going to happen? It's going to be equal to a constant, right? So this early condition is equal to a constant. And now we change the conditions. They're equal to the same constant, right? Right. So in mathematics, we know that if A is equal to B and B is equal to C, then A is equal to C. So that's why P1V1 equals P2V2. What you have to do when you're solving problems is first recognize, is this what I call a before and after problem? And if it is, what are the before conditions? What are the after conditions? So that's why when I read a word problem, right? When I read a word problem, I set up a table. And I put values in here. There should be at least 3 values, and we can leave one of them out, and that means we can solve for it, right? Any equation where you have a number of unknowns, if you know all the values for the unknowns except for one, you can solve for it. All right? So this is just a representation of what happens if we double the pressure, right? If we go from 1 atmosphere to 2 atmospheres, then we're going to take half of the volume. We're going to go from 1 liter to a half liter. If we go 4 times the pressure, we're going to have 1/4 of the volume. All right? Okay. So here's a problem. Word problems. Always remember, word problems are designed to confuse. They're designed to confuse because if you don't understand the concepts, then the problem will make no sense to you. You will not be able to solve it. That's the whole purpose of a word problem, to confuse you unless you know, unless you understand the concepts. If you understand the concepts, then we can extract information from the word problem and solve it. So a sample of helium gas occupies 12.4 liters at 23 degrees and 0.956 atmospheres. What volume will it occupy at 1.2 atmospheres, assuming the temperature stays the same? All right, so all we need to know is that the temperature doesn't change. And the gas is confined. We're not going to add any gas to it. We're not going to take anything away. So these two are constant. That allows pressure and volume to change. All right. So we recognize this as a before and after condition. You're given before conditions, volume and pressure, and you're given one of the after conditions, pressure. So we're looking for volume. So we got P1, V1, P2, V2. So the first conditions, pressure is 0.956 atmospheres. At what volume? 12.4 liters. And then we're also given the after pressure, 1.20 atmospheres, and there's our unknown. So if we set up our equation, P1 V1 equals P2 V2, then we solve for V2. Now we can confidently insert values into this equation and solve it. Let's see, P1 is 0.956 atmospheres. V1 is 12.4 liters. And P2 is 1.20 atmospheres. All right. So that's the thinking part. The rest of it is just number crunching. 0.956, oops. 0.956, 12.4, and 1.2. And I get three significant figures rounded off 9.88. What's the units of measure? Liters. Okay. There you go. Okay, now we're going to, we're going to another law. This is pressure volume. Now we're going to look at Charles' law. It relates volume and temperature. So if we let these two vary, then this one has to be constant, and this one has to be constant. Okay? So we want to know the relationship of volume and temperature. Charles came along about 100 years after Boyle. And the reason for the gap was there was no reliable way to measure temperature until Charles came along. So what Charles did was he took a gas, he took any gas, and he, how do you, all right, let's ask this question, answer this question. How do you maintain a constant pressure? The constant moles is easy, right? You just confine the gas and you don't let any in or out. But how do you do the pressure? The pressure is best if you have a uniform diameter cylinder, right? We have a cylinder down here. and you have a piston in it, right? And you apply, say, a 1 kilogram mass on it, right, to maintain pressure. Okay, so the gas is in here, 1 kilogram, and then you maintain the temperature, also, you maintain the number of moles and the pressure constant. So, and you can measure the volume because you can measure the height here. And height in a uniform cylinder is a measure of volume. Okay, so how do you change the temperature? Well, you enclose this device in some type of control. You blow cold air in or hot air in, or you have a liquid, right? A liquid here. And maybe you have a flame. And you just heat it up and you measure the temperature, right? You have a thermometer here. And you measure the temperature. And as the temperature changes, you measure the temperature, check the volume. And if you plot the volume against temperature, what you get, right? We're changing the temperature, so that's the x-axis. And we're measuring the volume. That's the y-axis. And if this is in degree C, each gas responds differently. It follows the same conditions. Right? Volume divided by temperature equals a constant. Right? As temperature goes up, volume has to go up. This is a direct proportion. So depending on which gas you choose, you could measure points in here like this. Temperature goes up, volume goes up, and we can draw a best fit curve to those points, right? We don't have anything out here. We don't have anything up there. So we could extrapolate. We could say, let's keep going. Keep going, keep going. And if we do that, and we say, all right, what would happen if, at what temperature would the volume be zero? Now, this is an ideal gas. We know that the volume will never be zero because gas molecules have volume. They have mass and volume. But theoretically speaking, we would get down here to minus 273 degrees C. That's known as absolute zero. And that's the starting point for the Kelvin system. This would be 0 K. This would be 0 C, which would be 273 K. All right. All gases follow this process, right? And they end up at this point. Even if you start up here or down here, they will end at the same point. But the relationship is volume divided by temperature is a constant. The slope of the line is positive. Right? Lower left, upper right, it's increasing. That's a positive slope. And that represents a direct proportion. All right, there's our absolute 0 point. Now, we need to use temperature with Kelvin units for one very simple reason. If we try to use this formula with degrees Celsius, at some point, those degrees are going to switch signs. They're going to go from positive to negative. And if they go from positive to negative, then our relationship is ruined. right? It won't work anymore. So we need a system that has only positive values for temperature, and that's Kelvin, because Kelvin starts 0 and only goes positive. So that's why temperature must be in Kelvin. Degrees C plus 273 equals Kelvin. All right. Let's see. You can use the 0.15 if you want. For most applications, you don't need it. All right. For the same reasons as Boyle's law, V1 over T1 equals V2 over T2. And that's the best formula for applying Charles' law is before and after. V1 T1 versus V2 T2. Okay, so here we got an example. So let's see if we can solve a problem using Charles' law. You have a balloon that's 1.3 liters of air at 24.7 degrees. You place it in a dewar. What's a dewar? A dewar is like a fancy vacuum bottle. It has very good insulating properties. So we can hold this liquid nitrogen at minus 195 degrees Celsius, and it only evaporates slowly. So what will be the volume of the sample of air when it reaches minus 195 degrees C? Right? So V1, T1, V2, T2. So the before conditions are initial volume is 1.3 liter. Initial temperature is 24.7. Final volume is unknown. Final temperature is minus 195. Okay? So we've got our known values placed where they need to be. We just need to convert. All right. So 273 and 24.7 is 297.7 K, and 195 subtracted from 273 is, we'll try that again, 273 minus 195. Oops. There we go. This is 78 K. Okay, now we can apply it to our formula. We know that V1 T1 equals V2 T2, and we want to solve for V2. So V2 equals V1 T2 over T1. Now I'm going to leave the units off because it takes up too much space. If we put them in the right place, we should be fine. 1.30 T2, 78, and T1, 297.7. Now, what are the units of volume going to be? Volume is going to be in liters. So let me see, I got that one, and 1.3 times that, and then 297.75, and I get 0.341 liters. So, and the last question you ask yourself, does it make sense? Well, if we're going to make it really cold, and it starts here, it ought to be a lot less volume once we get it cold. And it is. So our answer makes sense. Okay? Now, The next law on our agenda is Avogadro's law. Let's see. That. Avogadro. Avogadro's law draws a comparison between volume and moles. So this one has to be constant. This one has to be constant. Okay? So how do we do that? Well, you need that cylinder again with a movable piston. So the pressure is going to be constant, right? We could put a 1 kilogram weight on it or just let the atmosphere push on it. And the temperature has to be constant also. So if our lab space is relatively uniform atmosphere, then it's going to be constant for the duration of the experiment. Or you could submerge it in ice water, and that would be exactly 0 degrees Celsius. Okay, the temperature is constant, pressure is constant. And what we're going to do is introduce a gas in there in terms of number of moles, right? So if we have 1 mole to begin with, and then we put another mole in there, we have 2 moles, the volume is going to double. If we put 3 moles in there, the volume is going to triple. So that's the relationship of volume to moles equals a constant, right? That's a quotient equal to a constant, which means direct proportion. And we can write it that way, or we can write it this way. V1 over N1 equals V2 over N2. Okay? And that's the before and after applied equation. All right, so here we have, you can assume this is before and after. 2.45 moles of argon gas occupies 89 liters. What volume was 2.1 mole of argon occupy under the same conditions of temperature and pressure? So we have V1, N1, V2, N2. Right? What's the question? What volume after volume? There you go. Under these conditions, we're saying it's 2.1 moles. Whereas we had 2.45 moles to begin with, occupying a volume of 89 liters. Okay? So now we can solve this one for V2. V2 equals V1 N2 over N1. So now we can put the values in. I'm going to leave the units of measure out for convenience. 89.0 and N2 is 2.10 moles and then 2.45 moles. So 89 times 2.1 divided by 2.45. And that's 3 significant figures would be 76.3 liters. All right. So that's Avogadro's law. Now, Avogadro didn't propose the law exactly like this. He published a treatise or paper that discussed these relationships. It wasn't until he was followed by, it might have been Gay-Lussac or maybe Cannizzaro, they put it in this form, but they gave Avogadro credit for it because he came up with the original idea. Those are the days when scientists were reasonably honest. Okay, before we get to ideal gas law, I want to give you a combination of the three laws that we've discussed so far. Boyle's law. It says that P1 V1 equals P2 V2, correct? Okay. If we introduce Charles' law into this mix, then V1 T1 equals V2 T2. Now we have a combined gas law, but we can also introduce moles because V1 N1 equals V2 N2. So now we have a combined gas law. And we can let all of them vary, right? We don't have to hold any of them constant. We can let all of them vary as long as one of them is the unknown and we have values for all the others, we can solve for that one unknown. Or if we're going to hold them constant, say we hold V and T constant, volume and temperature is constant, then the relationship of pressure and moles is a solvable problem. All right. Each one of these that I added in is equal to a constant. So we can combine all those constants into a single constant, right? This is going to be equal to a constant. This is going to be equal to a constant. And we can say these both are equal to a constant. Okay? So, if we know that value right there with certain units of measure, and we know three of these, then we can solve for the other one, and we don't have to know before and after. We just need to know its current state. So if we take them together, PV over NT equals K, and we give K a special symbol. We change it to R. And if we know what R is, then let's solve it in a linear fashion. What you'll see most often is this one, PV equals, take the NT over here, nRT. That's the ideal gas law. Now, if pressure is in units of atmospheres, say it's 1 atmosphere. Volume is units of liters, and we know that under these conditions, where N equals 1 mole, and temperature is in Kelvin, right? Standard temperature for gases is 0 degrees Celsius. So this would be 273 Kelvin. Liters would be 22.4 liters. Those are the conditions that would prevail with those units of measure. And if we solve this whole equation for R, then R becomes 0.08206 liter atmospheres per mole K. Okay? That's one expression for R. And that's the only number that fits with those units of measure. If we change the units of measure, then this will change also. But this is the one we're going to be using. And whenever you use this equation, you have to be sure your units are in liters, atmospheres, mole, and K for temperature. Okay. Now, What type of problem is this? Is this a before and after problem or a state problem? Right? We know what it is right now. We don't know how it got there or where it's going. An automobile tire at 23 degrees with an internal volume of 25 liters is filled with air at a total pressure of 3.18 atmospheres. How many moles of air are in the tire? So we take this formula and we say we need these values, P, V, N, T, and we know what R is. 23 degrees temperature, we got that one. 23 plus 273 equals 296 K. This is the one we don't know. We want to find out how many moles are in that tire. 25 liters volume. Right? Correct measurement, correct value. Pressure is 3.18 atmosphere. That's correct also. So now we can solve this equation for number of moles. N equals PV over RT. So pressure is correct in atmospheres. Volume is correct in liters. R is 0.08206 liter atmospheres per mole K, and K is 296. That will give us the number of moles in that tire. And I get three significant figures. 2.7 moles. Okay. Here we go. So this is what I call a state problem versus a before and after problem. All right, let's see. Let's break this. We're doing on time. It's 10 o'clock. And we'll leave the rest of them up here like this. There we go. All right, for this problem, we want to know the pressure in the tank. If the volume is 304 liters, we know that there are, no moles, but we do have mass, 5.670 kilograms. Mass, 5.670 kilograms of helium in that tank at 25 degrees. And that's 298. Okay. All right. Can we get moles from that value? Sure. Right? Molar mass of helium is all we need. Conversion factor. But 5.670 kilograms is in the wrong units. Molar mass is grams per mole. So we need grams here. We have 1,000 grams per kilogram. Okay? And then we need to convert grams to moles for helium. Helium is 4. Two significant figures is 4. Okay? So if we take 5.670 and multiply it by 1,000, divide by 4, we have 1.4175 times 10 to the third. 1.4175 times 10 to the third mole. Now we can solve it. We solve for pressure. nRT over V. Number of moles, 1.4175 times 10 to the third. R is 0.08206. T is 298 K. And volume is 304 liters. So this pressure is going to be in atmospheres. And let's see. Let's say it's about 114 liters. Excuse me, pressure, atmospheres. Sorry, atmospheres, pressure. There we go. That's a lot of pressure. Okay, so here we are converting to moles. Here's the gas constant, here's temperature, and there is volume. And the pressure is 114 atmospheres. Okay? All right. Got another exercise. Let me see if we got time to do that one. Let's see if we're coming along okay. We have to step it up. I'm not going to put this one on the board. I'm just going to talk about the slide. Let's see. Oh, I forgot to mark this one out. Right. Exam 6 is due today. At what temperature does 121 milliliters of CO2 at 27 degrees C and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? Okay, so we're asking for the temperature. At what temperature? So we have conditions, 121 milliliters of CO2 before at 27 degrees and 1.05 atmospheres. If the volume changes to 293 milliliters and the pressure now is 1.4 atmospheres, this is a before and after problem. So if we use the combined gas law, and N is constant, right, we need the before and after approach. We're getting there. There's the before and after. Notice that number of moles is not there because moles is constant. So we pull the moles out. And now we're going to solve for, what do we need to know? At what temperature? Final temperature, T2. So solve for T2. There are all your values. You had to convert. You don't have to convert volume to liters because they're ratioed. They will cancel. Atmospheres will cancel. Temperature must be Kelvin. So now we have T2 in Kelvin is 969. At what temperature in degrees C? Well, we have to subtract 273 degrees from it. Now we know that the temperature is 696 degrees Celsius. All right. Now for another gas law. This was proposed by John Dalton. Partial pressures. Okay. What Dalton said was, if you measure a pressure, total pressure for a mixture of gases, then that pressure is the sum of the individual pressures of the component gases if they were separate from one another. So if we have this gas is a given pressure if it's in a separate container, and this gas has its pressure, this one has its pressure, on out to however many, it doesn't matter. But when you combine them, their pressures are additive to give you a total pressure. Now, what value is that? Well, what we learn is that these pressures are related to the number of moles of gas, right? Because we have P V equals nRT. And if we ratio the P and the N, right, and put the R, T, and V over here, then if this is a constant, then the pressure and the number of moles are related to one another. They're directly proportional. So what this says is this relationship is the total number of moles equals the moles of 1 plus the moles of 2 plus the moles of 3. Oops. They're related to one another. So if we know the relationship of the moles to the total, or if we know the pressure relationship to the total, then we know the proportion of each. In other words, if we said P1 over total, then we also know that that's N1 over the total. Right? That ratio, it's an intensive property. That ratio is the same for both of them. They're related, directly related to one another. This is just an example. If you have 1.75 moles of helium at 8.4 atmospheres and the given temperature, then you can have that same pressure if you, instead of having helium in there, you have helium, nitrogen, and neon, but they add up to the same number of moles. The total moles will give you the same pressure. And one of the things we must assume in this process is that the volume of the particles is not significant. They're so small, the volume of the particle is so small related to the size of the container and the distance between the particles that it's insignificant. That's why gases behave similarly. All gases behave similarly. Okay? We also have to assume that there's not any interaction between the particles. In other words, when two particles come at each other and slam, they don't attract, they don't repel. There's no force interaction between the two. What you get is just two billiard balls bouncing off each other. It's purely a physical interaction. Now, that's an assumption. That's an ideal situation. We know it's not true. But under certain circumstances, it's very close to the truth. If the temperature is high enough, that is, energy is strong enough, right? They don't have time, they don't have the energy of attraction or repulsion is not big enough to influence that collision. So that's high temperature. Low pressure means that they're infrequent collisions. So high temperature, low pressure will give you ideal conditions. All right. So here's a practical application of Dalton's law of partial pressure. Say we're heating potassium chlorate. And when you heat potassium chlorate, let's put it over here. if you heat potassium chlorate, right, and we use a delta, that means we add heat to it, you get potassium chloride plus oxygen gas. And that way, with this mole relationship, we can collect the oxygen and determine how many moles we started with. So the best way to collect a gas from an experiment like this is to confine it to that space and force it into a container which is filled with water. So here we have a water trap, and oxygen is being collected over here. All right. But what is in that gas space? Well, the gas space, the total pressure, is due to the pressure of oxygen plus the pressure of water vapor. Okay? So we can measure the total pressure. The number of moles would also be a proportion. Let's see, total moles would then be oxygen and water. But remember Avogadro's law? He said that the volume is proportional to the number of moles. So the total volume is also equal to the volume of oxygen plus the volume of water. Okay, and there's the reaction. All right, what we need to know is what is the pressure of water in that container? And fortunately, the vapor pressure of water is very predictable relative to temperature. So if we know that the temperature is, let's see, what was the temperature before? Doesn't say, does it? Okay. So if we rearrange this, we find that the pressure due to oxygen is the total measured pressure minus the water vapor pressure. And if we know the temperature, we can determine the water vapor pressure from this table. Okay? That's as far as we're going to go with that problem. There are a number of examples that you can work on in the review document that will take you further with that one. Now let's use the Dalton's law of partial pressures to solve this problem. Suppose we do have a container here, has a valve in the middle, and it's connected to a smaller container. And the gas inside this one, before we open that valve, the gas in here is 2 atmospheres pressure and 9 liters. But the gas on this side is 3 atmospheres pressure and 3 liters. Okay. The question is, what's the total pressure of this gas? We're saying it's helium, but it doesn't matter really. Any gases will do. What's the total pressure? Yeah. What's the total pressure after we open the valve? Okay. We can do sort of a semi-quantitative approach first to see the ballpark figure. If this one's 2 atmospheres and that was 3 atmospheres, is the pressure going to be any higher than 3 atmospheres? No. It's going to be higher than 2 because 3 is higher than 2. But when you mix them together, the pressure is going to be between 2 and 3. It won't be over either of those values. Well, it won't be over 3. It might be over 2, in between. So the pressure is going to be between 2 and it's going to be greater than 2 and less than 3. Okay? How do we solve this problem? Well, since Dalton said that this one, we can use Boyle's law and expand this one into that space and ignore the other one. So what would happen if this were a vacuum? If that were a vacuum, then we would use Boyle's law, right? We would use pressure, volume, pressure, volume. So the initial pressure is 2 atmospheres. The initial volume is 9 liters. What's the final volume? Because we don't know what this one is. The final volume is 9 plus 3, 12 liters, right? So P1V1 equals P2V2, and we're looking for P2. P2 equals P1V1 over V2. So the first contribution of this gas to the total is solved by this problem. Right? So this is, let's see, P1 is 2, and then V1 is 9, and V2 is 12. Right? So this is 18 divided by 12. 1.5 atmospheres. Okay? That's from this side. Now, if we go to the other side and say this is a vacuum, make that the vacuum, and find out what that contribution is. So P1 on this side is 3 atmospheres. V1 is 3. P2 is our unknown, and V2 would be the same, 12 liters. Now we can put in 3 here, 3 there, and 12 there. So it's 9 divided by 12 is 0.75. So 1.5 is the contribution from this side, 1.5 atmospheres. Contribution from this side is 0.75 atmospheres, 0.75 atmospheres. Okay, so the total is the summation of 1.5 plus 0.75. Is 2.25 atmospheres. Total pressure when you open that valve. Okay, that's the left side, 1.5 atmospheres. Open the valve, and what does the right side do? The right side then contributes 0.75 atmospheres, and the total is 2.25 atmospheres. Right? Let's see. I got till 11, I think. Yeah. Time. Yeah. I'm not going to put this one on the board. 27.4 liters of oxygen at 25 degrees and 1.3 atmospheres, and 8.5 liters of helium gas at 25 degrees C and 2 atmospheres, pumped into a tank with a volume of 5.81 liters and 25 degrees. Okay, temperature is the same for all of them. 25 degrees, that's a constant. So we don't have to worry with that one. We've got liters and atmospheres, liters and atmospheres. What's the new partial pressure of oxygen? Well, if you have oxygen gas and helium gas together, then you only have to consider the oxygen gas as it moves into a different volume. and then the partial pressure of helium, then we can add them together. All right, so the first one, we're going to calculate oxygen as a before and after procedure, right? Boyle's law. We get 6.13 atmospheres for the oxygen gas. Then we do the same thing for helium, right? It goes into the same final volume, and then we add them together. And now we know that the total pressure inside that tank after we add those gases is 9.06 atmospheres. All right, this is just a review to remind you what a law is and what a theory is and what they're designed to do. Remember that law is simply a generalization of observed phenomenon. If the systems are sufficiently similar from one situation to the next, you can use the law to solve the problem. But if you're significantly changing the conditions, then you need a theory that will help you understand how to modify your approach. And that requires that you understand why things are happening. Theories usually have models associated with them. We propose models because the models then, once we have a model that we can work with, then we can change conditions in the model and see what effect it has on the outcome. You can't do that with a law. A law is just a single set of conditions and you're stuck with them. But remember, when we make a model based upon a theory, this is an approximation. This is not reality. This is only an approximation of what we believe to be occurring. Now we're going to apply a theory to our gas laws and say, why do the gas laws behave the way they do? And that's where we go with the kinetic molecular theory of gases. That helps us understand why. These are the starting points. These are postulates. These are assumptions that we begin with. Gases consist of very tiny particles, atoms or molecules, right? That's not a big leap. These particles are very, very small compared to the distance between them, right? There's a lot of empty space in a gas. So consequently, we can assume that these particles, even though we know that they have mass and volume, we can assume that that's insignificant for many of our conclusions, the conclusions we draw from the gas laws and from our kinetic molecular theory. These particles, even though they're small, they are moving very fast and they're moving with random motion. Now, why do we say random? Because if you know a particle's here and then it's over here in a split second later, then, right, you know what the velocity is. But when we're dealing with something that small, we can't track every particle. Because if you have even a mole of gas in a container, that's 6.022 times 10 to the 24th of them. How do you follow that many particles, right? You can't. Not even a supercomputer can do that. So we apply a statistical method, and we say the particles are in random motion. So we get an average effect from that random motion. We also say that even though they're moving randomly, as far as we're concerned, they do impact one another, and they do impact the walls of the container and display on our device a pressure. What that means is that even though we assume these particles have negligible mass and they're not and volume, they still have kinetic energy because they do have mass and they're moving very fast. So a combination of all the forces, the impacts of all those moles of gas registers a pressure. We have to assume that there are no interactions among the molecules. In other words, like I said before, they act like billiard balls. When they smack into each other, they just bounce off. No attraction, no repulsion forces. What we also have discovered is that temperature is a measure of the average kinetic energy of the particles. Now, we can't easily do a direct calculation. If we know the temperature, we can say, all right, the kinetic energy is so many joules. Right? We don't do that. We just say that the temperature represents an average kinetic energy for the gas particles. So if the temperature goes up, their kinetic energy is increasing. All right. So there's an expression of kinetic energy. For any object, we can calculate the kinetic energy if we know the mass and its velocity. We square the velocity. Now, if this mass is in kilograms and the velocity is in meters per second and square it, then the units over here is joules. So as the temperature increases, we also get an increase in pressure. That's why, as the pressure increases, if the force is constant and we change the temperature, then Charles' law, that explains Charles' law. Increase the temperature, you increase the kinetic energy, which pushes more on that movable piston and gives us more volume. So that's a kinetic molecular theory explanation for Charles' law. That's why Charles' law works. Okay, let's check concepts here. You have two balloons, right? One has helium in it, the other has hydrogen in it. So that means that they're both under the same atmospheric pressure and the pressure of the expanded latex in the balloon. But the pressure is constant. Complete each of the following saying whether they're different or the same. All right, so the next slide says, the pressure of the gases in the two balloons are what? They're exactly the same. Why? Both balloons are in equilibrium. Their pressure is equalized with the external pressure. Right? They have the same volume. They must have the same pressure. All right, next one. Temperature of the gas in the two balloons is constant because they're in the same space and they're subject to the same external conditions, which influences their internal conditions, and the temperature is exactly the same. All right. How about the number of moles of the gas in each one? Well, Avogadro says if the volume is the same, the number of moles must be the same. All right. Now, how about this one? The density of the gases in the two balloons. Remember what density is. Density equals mass per unit volume. All right. The volume, let's see, this is helium and hydrogen. Volume's the same, right? Volume's the same for both of them. Right? And the number of moles is the same. But if you have the same number of moles, what's the mass? The mass of helium is about twice that for hydrogen. So the mass is going to be doubled. That means the density of helium is approximately the density of helium is approximately twice the density of the hydrogen. Because the individual particles of helium are twice the mass of the particles of hydrogen. Okay? There we go. Sketch a graph of pressure versus volume at constant temperature in moles. Right? Looks like that. Right? That's Boyle's law. And it will always look like that. About volume and temperature. There you go. Direct proportion, positive slope. About volume versus moles. Oops. There we go. As moles increases, volume increases. That's Avogadro's law. All right. Let's see. Okay. Concept check. The volume of the neon balloon is twice the volume of the argon balloon. So in mathematical terms, we say the volume of neon equals 2 times the volume of argon. Now what? Which of the following best represents the mass ratio of neon and argon? So let's see, neon is here, and argon is here. So the volume of the volume of the neon is equal to twice the volume of argon. Okay, mass ratio. Well, first of all, what does this tell us about the number of particles in here? Well, the number of particles of neon should equal to twice the number of particles of argon. Okay? If we're going to ratio the masses of the two, say, what's the mass of neon ratio to the mass of argon? Look at the molar masses. If we have different numbers of moles and the molar mass of neon equals about 20 grams per mole, and the molar mass of argon is about 40 grams per mole. Right? So if you have twice the volume of neon, you have twice the moles of neon. So twice the moles of neon, say you have 1 mole of argon, right? If you have 1 mole of argon, you have 40 grams, right? 1 mole of argon. How many moles of neon do you have? You have 2 moles. 2 moles of neon would weigh 40 grams. 2 moles of neon weighs 40 grams. The ratio of their masses is 1 to 1. All right. Let's see. Another problem. You have a sample of nitrogen gas, N2, okay, in a container fitted with a piston. The pressure is 6 atmospheres. Gas is at 45 degrees in a volume of 6 liters. You then cool the gas sample. All right, what's going to happen? If you cool the gas sample, what happens to the pressure? Nothing. It's the same pressure. But if you cool it, the volume is going to decrease. Charles' law. Pressure of the gas doesn't change. Volume of the gas decreases, according to Charles' law. So, with this gas sample, we're going down to 15 degrees. Charles' law. Right, so we have 6 liters to begin with. We have a new volume that we don't know yet. The temperature in Kelvin is 45 plus 273 to begin with. Afterwards, it's only 15 plus 273. So we find the volume then has decreased from 6 to 5.43 liters. So what's the molar volume of an ideal gas? Actually, I already gave it to you. But if we know what the constant value R is 0.08206 liter atmospheres per mole K. Standard temperature for gases is 0 degrees in 1 atmosphere. That's only for gas laws. Standard temperature for any other chemistry problem is 25 degrees Celsius, but for gases, it's 0. So what's the volume? If we solve the ideal gas equation for volume and we plug in the values, right, then we get 22.4 liters at standard temperature and pressure. Okay, a sample of oxygen gas has a volume of 2.5 liters at standard temperature and pressure. How many grams of oxygen are present? So how do we get to that one? Right? We don't have a gas law that works in grams, but it does work in moles. If we can determine the moles of oxygen at standard temperature and pressure in 2.5 liters volume, then we can convert moles to mass using the molar mass. And that's what we're going to do. Well, actually, we made it even simpler, right? That just goes to show you can solve a chemistry problem more than one way. Since we know that the molar mass, molar volume is 1 mole equals 22.4 liters, we can convert the liters to moles. Then we can convert moles to mass. Actually, that's much easier. This is the second procedure that I was getting into at the beginning. So this will tell us the number of moles of oxygen, and then we can convert that to mass. Same answer, different procedure. So here we have a reaction where we put zinc and hydrochloric acid together. It produces zinc chloride, right? Yeah, produces zinc chloride and hydrogen gas. So if we take 15 grams of zinc and 100 milliliters of 4 molar hydrochloric acid, what volume of hydrogen gas is produced at 25 degrees in 1 atmosphere? Well, first, we say we want to know the amount of product. If we have 15 grams of zinc and we determine that its moles is 0.2294 using the molar mass, And we have to assume that the hydrochloric acid is excess. That's what we've done here. Then we can use our coefficients to convert moles of zinc to moles of hydrogen. As it turns out, the same value, because all the coefficient between zinc and hydrogen is 1 and 1. So now that we know the moles of hydrogen, let's see. Oh, my mistake. We do need to determine the limiting reagent. And the limiting reagent actually turns out to be hydrochloric acid. All right, so we have some zinc left over, and we use up all the hydrochloric acid. So now we have our ideal gas equation, PV equals nRT. We solve for volume because we know 1 atmosphere is standard pressure, 298 K is standard temperature, and we have determined the moles of hydrogen, and K and R is a constant. And we find that we should have 4.89 liters of hydrogen produced from this reaction. Okay. One more concept. When we say Boyle's law, let's see, PV is a constant. All right? Pressure times volume is a constant. If we plot this data on a graph, we get a hyperbola. Like that. Scientists don't like curves. We deal with them when we have to. But if we can do something to the data to produce a straight line, that's much preferred. So how do we do that? Well, look what happens if we have a data set here. If we have a data set where we've measured pressure and volume, right? We have values here, values here. What if we rearrange this equation? Let's just say P on this side and V on that side. How about that? That's allowed. Math allows me to do that. Well, I don't like it that way. Let's separate them out. Let's say K here times 1 over V. Okay? This is a constant. These are variables. What does that look like? It looks like Y equals M slope mx plus B. Straight line. Well, what's B? Well, B is 0, right? That means that if we plot pressure against 1 over V, right? We plot those instead of this, we'll get a straight line that goes through the origin, because that's B, 0. Y-intercept is 0. Okay, so all we have to do is transform, take the inverse of the volume and plot that data, and we get a straight line. That's great. Actually, these two plots are wrong, right? Because pressure is not a dependent variable. Pressure is the independent variable. So we need to flip the axes. But you get a straight line. Now, if we use this graph to read off data, say, what if I say, if I want the pressure here, what's the volume? Go up here, go across here. That's 1 over V. So once you get 1 over V, you have to take the inverse of it to find the volume. What are the units of measure? Well, let's say this is atmospheres, possibly. If volume is liters, then liters to the minus 1 is unit of measure. Why? because whatever you do to the number, you have to do to the units also. And liters to the -1 is inverse liters. All right, that's it. Stop the share. And let's see what we'll do next. Since we finished the lecture, next Tuesday, I'll take the review document like is customary for this semester, and we'll work the review document for some of the problems that I've picked out. If you zoom in, then you can hit me with any problem you want, and we'll solve it. And then we'll probably finish on Tuesday, which means the following Thursday was listed as a review day. On the buffer day, we're gonna do the review. So that way on the review day, I'll just zoom in from my office, and if you need me, you can zoom the class period and we can discuss any problems that you have. That means that the exam on this material will still be on April 14th, right? So that's 12 days. 12 days? Yeah, 12 days on a Tuesday. All right, that's it for today.